You spend weeks wiring your DIY robot. You write the code for obstacle avoidance, integrate a Bluetooth module, and throw in some custom lighting also, along with animations. It works perfectly in isolation. But the exact second you try to run all of these features at the same time, the system freezes. And sometimes the system falls apart. The Bluetooth connection drops, the motor freezes up, or your robot completely ignores an obstacle and smashes straight into a table leg. Here is the dirty secret. Your hardware isn't broken. Your code has just trapped your microcontroller inside a chronological prison. To understand how to break out of this loop, let's look at the underlying architecture and learn how to build a firmware system that actually multitasks. Most beginner tutorials teach you to control timing using one single command, delay. It seems completely harmless. You want an ultrasonic sensor to wait between pings or a servo to pause, so you tell the processor to wait. But when an 80 mega 328p hits a delay statement, it doesn't just wait. It completely paralyzes the CPU. For those 500 milliseconds, the clock cycles are wasted doing absolutely nothing. The processor is functionally not working, or functionally you can say dead. Just think about what happens to your robot during that tiny fraction of a second. It cannot read incoming serial packets from your custom Bluetooth app. It cannot process distance math. If your motors are running forward when this delay hits, your robot drives completely blind until the timer expires. The moment you try to stack manual control, autonomous obstacle avoidance, and active telemetry tracking, these delays cascade. The serial buffers overflow, the logic desynchronizes, and your robot freezes. So, to fix this, we have to burn the delay function to the ground. To build a reliable platform under real-world constraints, we shift to a completely non-blocking architecture using internal hardware timers. In the firmware for Nexus 1, everything revolves around a single baseline variable, current millis. Think of it like this. Imagine you are in the kitchen cooking dinner. You put a dish in the oven that needs to be baked for 30 minutes. You stand completely frozen, staring at the oven door without moving for half an hour. That is what delay does. Instead, you look at your watch, note the start time, and while the food is baking, you chop vegetables and wash the dishes. You are basically multitasking by pulling a stopwatch. This is exactly how millis function. Instead of halting the processor, the main loop of Nexus 1 executes thousands of times per second. Each single pass, it asks the stopwatch, has our interval passed? If no, it skips ahead instantly, and if yes, it executes the reading in a fraction of microsecond and then moves on. Because the loop never stops to wait, the sonar scans, the Bluetooth app pulls live telemetry data, and the motor output refresh concurrently, creating a system that feels fluid and organic instead of jerky and broken. Once your timing is non-blocking, you unlock the ultimate superpower of embedded system design, finite state machines. Instead of writing a massive unmanageable wall of nested if-else statements that constantly fight each other for control, the robot is strictly isolated into explicit deliberate behavioral states. By tracking our operations through a state variable, features cannot collide. In manual mode, obstacle routines are completely dormant. When you switch modes on the app, the state machine cleanly switches gears, reallocating timers and sensor routines instantly. Take our pet mode for example. Because the architecture is state-driven, the robot cycles smoothly between sleeping, acquiring a target, and calculating gradual steering corrections without a single blocking interruption. Now that our timing engine is completely stable, we hit our next massive engineering constraint: motion. In the next video, we are diving deep into the physics of steering and how we achieved smooth organic analog differential turning out of cheap gear motors without a single encoder. Please understand, building an advanced robot isn't about opening your wallet to buy a faster processor or expensive hardware encoders to rescue bad code. It's about constant event engineering and clean firmware architecture. If you want to build systems instead of just copying tutorials, hit subscribe. Let's build better engineering. This is Nexus Tech Labs. I will see you in the next breakdown. Thank you.